Hello, everyone. Thank you for attending the Thermal Fluid Analysis Workshop vendor session. My name is Heston Bryant. I'm one of the newer engineers here down at Kennedy Space Center. I'm part of the Launch Services Program, NASA's Launch Services Program, and I'm on the thermal team. And here today we have Bruce Crawford presenting some work he's done with Ansys for Ansys on high fidelity simulation of thermal protection systems. Very excited to see this. This is a pretty important part of space flight, I'm sure as many of you know, and it's a challenging problem to address. So, Bruce, go ahead, take it away.
I work as a senior application engineer at Ansys, specializing in aerothermal and combustion modeling. Today we'll be talking about the ablation capabilities in Ansys Fluent. The latest version is 2022 R2. So what we're going to discuss in this presentation is, the process of ablation with different aero systems and requirements. We'll go through the current modeling capabilities at Ansys Fluent, to meet the needs of, everybody to simulate these type of processes. We'll go through the new ablation modeling panel available in 2022 R2 and the models available with that. And then we'll show some, couple validation case models available and that are used in testing. And we'll go through some future developments in the ablation modeling that we're working on. So ablation, why do we need to model this? Key thing, ablation is used throughout the aerospace industry for, thermal protection in different systems. For example, re-entry shielding on spacecraft, rocket nozzle cooling, etc. But ablation modeling can be used, to model burning of solid rocket fuel too in solid rocket modelers. So there's different ways you can look at it. Process, is a reaction or a physical erosion of the materials that, transports or removes the heat from the surface of the body, protecting, the body from higher temperatures than, that it can't handle. You can see all the different examples here on the slide, when changing center mat, what things that are important to when we model this ablation processes. So looking at this slide here, it's a kind of generalized physical process involved in ablation. Very complicated with heat transfer, chemical and physical flows as seen in the diagram with all the materials and flow interactions. Again, this could be applied for both external cooling, material ablation, SRM, solid recession burning, and also if there's other industries out there that use ablation, but right now we're just going to focus on aero industries for our case presentation. So over the last 20 years, Ansys Fluent has been used to model different physics that would need to model ablation. Again, we tackled different parts, individual parts here and there, do different things, adding, UDLs and specializing for special, projects for different customers. But what we needed to do is trying to take all the stuff we knew and, and generalize it and put it into a model setup, so people can access it very easily. So they, each user wouldn't have to reinvent the wheel. So we could take advantage of what we've learned, how to set up, recession models, different types of, particles, radiation, everything with it. And that's what the efforts have been over the last year and a half, trying to get this stuff so it's easier to set up, get some empirical models and try to adopt some of our chemical process, models that we have to try to get some structure around it, make it easier for setup. And also take advantage of our, meshing and, deformation and remeshing capabilities in the code to add that complexity to the model. So here you can actually see going through our set, you could turn on the ablation model, coupling automatically. That kind of switches things on internally. And then once you get that turned on, it adds a tab for which boundaries you want to put ablation on. And then you can actually set up either VL's law or surface reaction. And also, as you go down through, you can, see what you needed to set up. If you're going to use surface reactions, technically you have to input that in first so you can be able to select it for that boundary condition. So going down through the steps, as you can see here, my animations aren't working. So you can see the animations here. And then as you go through this process, we also have the capability now to, have VL's law set up. We can actually have mass flux from the surface based on some mass fractions we set up either as a constant, or we can set up it as expression based on temperature or some other function that will go along with the recession rate that's calculated from the empirical model. The surface reaction has that kind of built in, so it's already built into the mechanism for that to happen. So it implicitly calculates the species based on the surface air chemistry being used. Once all that's set up, you got your boundaries that you can select from. You know, now you got to go through and set up your mesh settings. It automatically gets set up for you, but it just doesn't know which boundaries you're going to be working with. So you would have to go in and select which boundary and find which ones you want to work with, because you can have different settings for different ones depending on the material, depending on which model you're working with. You can actually have surface reactions with VLs or whatever you want to do, depending on how you want to do it. And we have different ways of dealing with the dynamic mesh. We can smoothing, remeshing. We can take advantage of what's there. But default settings should give you some reasonable. There are some limitations. VL's law, was set up to deal with SRM, but there's other empirical models out, numbers out there to do different materials. With the latest versions, as I said, we can actually use mass fluxes into it and take advantage of it. But there are, we're not able to do particles as yet for what we want to do. We would have to use UDF still for that. There is some other, so there is some limitations, and there are also some limitations just with the density-based code with this. We can also switch, depending on the mock down, we could switch back to the pressure-based code, but we have some limitations in number of species we can work with also. I think we're limited to 50 right now with the pressure-based or density-based code. We're unlimited with pressure-based. Another key thing is kind of shows, a solid rocket motor, but the ability to do CHT with the ablation is kind of key, because you want to be able to model the heat flow through the solid into the structure, and you also want to see how the heat gets taken away during the flow processes. The CHT capability has been worked on a lot in the code in the last couple of years, and it's shown to work very good with a static mesh and with a high speed density based code very well. Here we're showing it working with multiple materials, being able to see that the gradients through the rocket. Next step is to put the ablation onto this. It works very well static. I've started testing now with doing the moving and deformation of both the fluids mesh and the solid mesh at the interface, and be able to change the meshes on both sides to be able to take effect the recession rates and the deformation going on in the process. Hopefully this will be ready in the pre-release coming in the next year. Here's a simple model from that we used for one of our test cases, and we've been seeing how it works with both VLs and the surface reaction, and doing the different modeling capabilities that we currently have. In this case, it runs pretty well. We can actually, the mesh I have set up with this with the polyhex core mesh with about 15 layers of fluid of ablation layers on the boundary layer mesh. It runs about, on my laptop for 4 cores, I can run 100 time steps in about 4 minutes, and I get a decent recession rate. It gets a few millimeters, or almost a centimeter of recession rate on the surface, just changing the terms to make sure everything's working and testing. But this is running, I can't remember what the Mach number is on this one, but it's a, real high Mach 3. We've actually bumped it up to a higher Mach to see how everything works too. And it's actually been implemented as one of our tutorials for setup, how to, start working with the ablation modeling capabilities. Again, another ablation is generic solid rocket motor. How to deal with that on the insulation material on the nozzle. This is another one we're trying to work with to see how we can implement it to work with the CHT and everything. This is one of our old cases, but again, as you can see here, it's density based, solver transient, compressible flow, ideal. Using K omega turbulence model, and second order. This one's running second order. We're working on our third order differencing right now to see how things work. So with our future modeling capabilities, your current ablation models, there's the first step, but through adding to the framework, we're going to keep building on the ablation modeling capabilities in Fluent. We plan on adding more physics for future releases to add the complexity of the flows, add it to improve the fidelity and the solution. So it's going to be a step-by-step process out adding the new capabilities, but moving forward with the development. But the issue is there's not a lot of data out there to do a lot of validation with. So hopefully we can get some, collaborations with universities in the future working on that to see what we can do. But the new features, again, are going to be based on the needs of the customers. We wanted to show what it is now, what we have, and hopefully start working together to, provide what they need. And again, future developments with SRM, we're always, trying to, put in more materials, complicated materials, how to deal with them, CHT, and we're also trying to get into pyrolysis reactions, porous media, so we can actually model it, closer to first principles. So hopefully this, help with the rocket modeling too. You can see that. Another part of the ablations we is trying, this kind of shows from a rocket point of view, but it was a major issue with one of our customers is how to model the ablation and the startup process in the SRM. But how they have no way of testing for this, so we were setting up some proof of concept models with FSI to be able to model both the solid fuel, the casing, and the gap to see if we can simulate what was going on during the startup process. With this case here, it's trying to find out where the hotspots are going to be, and then as we're going to add the ablation modeling to this to be able to do the recession rate properly to the models. This can also be reversed to the other side of doing reentry vehicles and be able to do that type of modeling. So again, with the two ablation models set up, so if between the VL's law model and surface reaction, again, this is capable to take advantage of all our meshing capabilities and doing 2D, 3D, however you need to do it for your modeling capabilities. It's been tested with what we have to be able to take advantage of that. Ablation model automates the dynamic mesh coupling setup, so it makes it easier for the user. You don't have to go and try to find everything. Everything gets set up automatically, and you just put in the key data points to make everything work. Again, some of these models are limited in capability. VL's law is limited in a way, but if you have surface reactions, we can take advantage of it up to a certain amount of species to make things work. But again, we need, looking for some more, validation cases so we can actually push it to the limit and see what we could do. Again, all this stuff runs on, multiple CPUs, and we can take advantage of different machines to make this work. And hopefully, with the future developments, we can really extend, really beefing up the fidelity for this type of model. And that's all I have for today. The other stuff I didn't cover in here is been doing a lot of work with high-speed air chemistry. So that can also be integrated in here too. We have a 2-temperature model built in now. So as you go, we can actually add that stuff as we go downstream. That's stuff I should have added in here.
We have a question here. Can the ablation solver be added directly into mechanical, or is it a combined fluent mechanical only?
Currently, everything's built into Fluent. So we do all the solid and fluid, modeling in there with CHT and Fluent. Can we couple with mechanical? As you saw there, we did the FSI. That is coupled with mechanical, and we do go back and forth between the fluid and solid solvers on that. We do have a intrinsic FSI solver in Fluent that I'm still testing. I don't condone using it as just yet, but it could lead to a way of doing this stuff and go faster too with doing internal FSI. So we're trying to see which ways better to do things. But I know I have had that asked before. How can we do ablation directly on mechanical, where we put all the information, but we have to model the flow information on one side to pass it to the other, so it's actually has to be coupled.
Yeah, I have another question too. So the layer that's receding, it looked like from those post-processing plots that it was really capturing a 2D or a 3D action within the receding material or the ablating material. Is that 2D, 3D, like there? It's not just 1D.
That's not 1D. It's all 2D, 3D. I didn't have it on here. I actually have a capsule in 3D showing the ablation, and it's uniform, but you can see it in a 3D form on the bottom. So you see how everything's going. All the cases I run are all 3D models, even though I'm only showing 2D on the side, just to make sure everything's working for 3D.
Mm-hmm. Yeah, that's fantastic capability. I'm pretty envious of that.
So, but we can also reduce back to 2D if we need to. I've run some stuff in 2D, but I try to do all my testing in 3D and make sure everything works.
Excellent.
Especially with the boundary conditions. We fixed a lot of the 3-stream boundary conditions to really help with robustness and speed.
And that the chemical species that you said you can address up to 50, that seems like plenty. Have you ran into many cases where that's limiting?
Yes, when I was trying to do some other combustion modeling, I was trying to use a full finite rate mechanism for